Sometimes there is a set date, but maybe out of time because I have another one somewhere just not here, and then I do it whenever.
Okay, good afternoon, everyone. It's a pleasure to introduce today's speaker, Professor Jürgen Blum from TU Braunschweig. And I was just talking to him about his CV, and I think I had to take note because it's so long already. He started his promotion in 1990 at the Max Planck Institute in Heidelberg. And of course, for the promotion, you have to work at the University of Heidelberg as well. He then was at Max Planck and the University of Jena. I think that's about the time we were possibly already met for the COSY project, which was the end of 80s, beginning of the 90s in Germany. He habilitated in 1999 in the University of Jena, and then switched over for some time to the Naval Research Lab in Washington, D.C., before he returned back to the University of Jena. And since 2003, he is professor at the TU Braunschweig, and that's where we now meet regularly. And we'll have a couple of joint projects by now, and hopefully one more soon. And enjoy the talk.
Thank you very much for the invitation. Thanks, Peter, for the nice words of introduction. Apologies, I wanted to be here last year. Due to so many strikes in Germany, I couldn't, but now I'm here, and I'm happy to give you my latest view on what comets may or may not tell us about the formation of the solar system. I see this nice poster here. This is the setting. So we're in a protoplanetary disk, and we're interested of how planets form in there. And we know from observations, it all starts with dust, it ends with planets, but in between are planetesimals. And planetesimals, for those who haven't heard about that word, is an artificial composite of planet and infinitesimal, meaning very tiny planet. So today, when I started this field many decades ago, a planetesimal was a 1 kilometer sized object. Today, a planetesimal is rather 100 kilometer sized objects, or anything in between 1 and 1,000 or so. So things have changed in time, but I'll tell you in just a few minutes. So I want to give you an overview of planetesimal formation. This is from a review we wrote a couple of years ago. What my perspective of how planetesimals, which are here on the right-hand side, this is the time, so 4.6 gigayears after the formation of the solar system, or when the solar system looked like that. What happened, starting at the top left, with dust particles at very small ages, immediately after CAI formation or so, and how it proceeded in the protoplanetary disk phase. This is what we're seeing here, which lasts a few million years, and what happened then afterwards on short and long timescales, and run you through these points one by one. And in the end, I'll explain you what kind of planetesimals we would expect in today's solar system if they had survived so long. And then I'll go over to comets and try to identify which possibilities can be matched by comets. So this is the objective of my talk today. So we start with step one, of course. So we take as a given that there is lots of dust particles that were inherited from the molecular cloud or freshly condensed in the protoplanetary disk, doesn't matter where they come from. So the canonical size is a micrometer, or maybe a little bit smaller than a micrometer. And what happens then is the dust comes together, first by Brownian motion, then by drift motions, turbulence in the gas may play a role. So there are collisions, and these collisions initially are relatively gentle, low velocity collisions. And as everyone knows from experience, dust sticks very well, if tiny particles stick very well in your household as well. The van der Waals forces, which are the smallest forces you can imagine, but they cannot be switched off. They are strong enough for these little particles to bind them into larger and larger agglomerates, first fractal, then non-fractal, and in the end, pebbles. So I would like to convince you that we have a pretty good understanding of what happens here. And we did a lot of experiments in the past decades to clarify this picture. So what you're seeing here is one of our many lab and microgravity experiments. In this case, it's a microgravity experiment in which we studied collisions among dust particles or agglomerates of dust particles at low velocity and in vacuum. So what you're seeing here is a stereo picture. You can either look at the left or the right. It's the same thing from two directions. I started again. And the one highlighted here in the middle is working, okay. Collides gently, typical collision speeds on the order of a few centimeters per second. That's the collision speeds predicted for protoplanetary disks, and forms larger and larger agglomerates. So the things we started with, so the tiniest black dots you are seeing here are these 100 micrometer clumps consisting of those particles which you cannot see, which are micrometer sized silica beads in that case. And we did really many experiments over decades. And in the end, we ended up with a dust collision model. So this is a complex endeavor. Just taking one of those panels. The panels are all identical in the meaning, but for different particle sizes or temperatures. So here, this is for micrometer silica at 1 AU. This is for nanometer silica at 1 AU. This is for water ice at 3 AU and water ice at 10 AU. And qualitatively, they're all the same. Quantitatively, they are different because as you go further away from the central disk into the outer ranges, the characteristic numbers, the Stokes numbers of the particles change because the density and pressure of the gas goes down. And so the contours change. So what you're seeing here is the size of one agglomerate versus the size of another agglomerate. And so any combination makes collide. And the contours here, which are the dashed lines you're seeing, give you the collision speeds in meter per second. So 1 meter per second is here. So this is the contour. All along those contours collide at the same 1 meter per second speed. And you're seeing typically the speed goes up as we go up in size. And the colors in the background are the results from our many laboratory experiments. If you're seeing the greenish colors, meaning collisions rather tend towards growth, so particles collide and stick to each other. If they're very red, they fragment, so they destroy each other. If they're orange, there's sort of destruction also, and the yellow is the bouncing phase, where particles just bounce off and nothing really happens. And really, many decades of work and labor go into this. I just want to stress this little piece here, which of course it's symmetrical, is also here, which we call the erosion barrier. And some time ago, we did some simulations of what happens if you painted all that green. So every collision leads to sticking, except for those which are eroding, abrasion or sandblasting, whatever you would like to call it. So we started, here is a size spectrum, and the different curves are at different times. And here is the frequency of occurrence. So we started at small particles, let it evolve because everything is green. So particles hit and stick and grow until some particles hit this corner here. And then they start fragmenting, producing little particles, which in turn enhance this. And so the whole growth stops at a size of about 10 centimeters here. So the biggest size, even if you paint everything green, is 10 centimeters. That tells us there cannot be any particle much bigger than that because of physical arguments. Yeah, there might be way rounds, but I don't want to discuss them in my main talk. If you have questions about that, you may want to ask later. But let's go back. But this is the reality here, so not the idealized case. So reality is worse than that. So if we do that in reality, how big of an aggregate do we grow here? And this was our first publication on that by Andras Schomm et al. It was actually a back-to-back 2 papers by Carsten Güttler and Andras Schomm. And what you're seeing here is the maximum mass one can achieve with different solar nebula models. And so the upper 2 solar nebula models obviously lead to 1 gram, meaning 1 centimeter aggregates, which we now call pebbles, whereas this model doesn't work, obviously. And a few years later, Sebastian Lorek did another study including ices. By that time, we had also worked with ice as a material. And you're seeing here as a function of distance to the central star, or the young sun. At 5 AU, the maximum mass is 0.1 gram, so just under a centimeter in size, and it goes down towards the millimeter. In the inner solar system, we think we understand the formation of pebbles of give or take a centimeter in size. In the outer solar system, of give or take a millimeter in size. And those we now call pebbles, although they're not rocks, they are fluffy agglomerates with some porosity. In other words, confirm this or are in contradiction to that, but that's typical for science. That's clear. So, question is, can we observe that? And the answer is maybe yes. In the realm of ALMA, we have these beautiful pictures of protoplanetary disks. So this was just the painting by an artist. Now reality has caught up with the artist's impression. So for instance, CW Hydra. And in the lower panels, you're seeing the estimated size from the analysis of different wavelengths. But you need, of course, models for the dusts and optical properties at these millimeter wavelengths also to interpret that. Here is a centimeter again. So you're seeing a centimeter is the canonical size. Also here, falling down into the sub-centimeter region, millimeter region here at 100 AU or so. And all these are very, very similar, at least qualitatively. Another work, concentrating on HL tau, one of the disks also on the previous slide, comes to similar conclusions. So a centimeter is here. In the inner 50 or so AU, centimeter in the outer 50 to 150 AU or so millimeter size. And here the model is of compact dust. And here the model is of very fluffy dust. And you see qualitatively they are almost the same, but quantitatively they might differ. So somewhat smaller dust particles here. In this concentration, the dust particles seem to be huge, which is very difficult to measure. So I doubt that exact number here. But you see, that confirms our estimates from laboratory experiments and modeling that you are able to grow protoplanetary disks, are able to form millimeter to centimeter size fluffy aggregates over the course of their existence, which is a few million years or so, particularly, of course, that's much shorter. Okay, so once we have them, we are hitting the bouncing barrier. That's what we called it. So after, if I go back to the model, so after we've reached a centimeter or so in size, which is here, yeah, we're hitting this yellow regime or this orange-red regime. So no more sticking, but just bouncing. If we would go further, then the particles will destroy. So this is the absolute upper limit we think there is. So the question is, can we grow planetesimals from here? And the old idea back into the 1980s or so was you need sticking collisions in order to form planetesimals. It was at that time already theoretically very hard to achieve this on the time scale of a few million years, which is the maximum time that the protoplanetary disk with the gas around exists. Once the gas is gone, no further growth, because then the collision speeds are extraordinarily large. But now we have mechanisms that form planetesimals out of pebbles. The idea is we do need to concentrate the pebbles spatially somewhat. And I'll show you in a movie on the next slide that hydrodynamics alone in a Keplerian shear disk are able to do that. And then an effect called the streaming instability kicks in. So once the concentration is high enough, then the pebbles collectively act together. So they move as a collection of material against the gas pressure. So the gas in the disk rotates somewhat slower than Keplerian. So if there's a single pebble, it is dragged along at sub-Keplerian speed, which leads to the radial inward drift. But if there's many, many pebbles, like the peloton of a bicycle race, the bicycle runners come together because only the front people take the headwind, and all the rest is in windless area, so it's much easier to fight against the friction, because the gas friction is taken by the front ones. And here, if the front ones take the gas friction, the other ones don't see the gas drag. They push on the front ones, and though the collection moves together at higher speeds, and that in turn is an instability, because that catches up with all these single pebbles and all the pebbles that radially drift inward, and that peloton here becomes more and more massive over time. And at some point, the Jeans criterion kicks in. So it's a criterion of gravitational instability. So the internal gravity of all those zillions of pebbles together is stronger than any disturbance, and the whole thing collapses and forms planetesimals. So that's the idea. So here's the picture again. So the pebbles come together. I show you two simulations. The left simulation, which will just start in a second, is both are from numerical simulations from Jake Simon in the USA. And here is just hydrodynamics. So we'll start with a protoplanetary disk. We're looking from in the z direction onto the face of the disk, so like vertical at a little piece. It's a shear disk, so more inward. The speed of the co-rotating frame is larger, and outward is slower than the co-rotating speed. And there's just pebbles and hydrodynamics, no gravity, nothing. Gravity of the central star, of course. And what you're seeing, we're forming regions of underdensity. So the underdensity is negative here in the logarithmic units. Start it again. And regions of overdensity, and you see the scale is almost 3, -3 and 3, meaning almost a factor 1,000 above average and almost a factor 1,000 below average. So those regions, and if I stop that just before the end, yeah. Over here, you're seeing these beautiful spots here of high concentration pebble clouds moving together, like the peloton of the bicycle racers in the Tour de France, for instance. Okay, now we do the same simulation, but now at some point we switch on gravity and the internal gravity of all the pebbles combined. And you're seeing what happens. So you're forming gravitational bound pebble clouds, which under their own weight collapse until the pebbles meet each other and form a single body. And it looks like the merger of galaxies here. And it's basically, because it's gravity driven, it's very similar. The exception is that there is, of course, a gas motion around the whole system. You see a merger here. So this is how, in the end, typically 100 kilometer size planetesimals form, which were formed out of the collapse of individual centimeter-sized pebbles or so. And there's more work done on that, on the theoretical part. So if you start not with a single-sized pebble, but you have a distribution of sizes, you can see here by the different symbols. And you look at the planetesimal that forms. You're seeing the larger pebbles are here in the center, the smaller pebbles are outside. You're seeing the same thing here as the size of the pebbles, the centimeters here, millimeters here. So from the inner to the outer part, the pebble size decreases. But that is not important for what I would like to say next. Okay, so now we have this collection of pebbles gravitationally bound to a single object. The question is, what happens with that object? So there is, of course, now gravitational pull on every pebble, particularly those at the surface feel the gravitational pull from all the pebbles inside, but those inside feel the weight of all the pebbles above. And the question is, what happens? And so we formed pebble piles in the lab. So every single white thing you're seeing here is a millimeter-sized pebble or so, again, consisting of micrometer-sized dust particles, again, silica. And And we simulated what happens in a planetesimal. So this is the lithostatic stress in the center of a pebble pile of radius r in kilometers. And for a 1 kilometer radius object, this is 35 pascals, which if you have a feeling for pascals is not a lot. But if we're at 100 kilometers in radius, which is the typical size of a planetesimal, so we're here at 10,000, so we have 350,000 pascals, which is at the end here of the scale. So we did experiments. We formed pebble piles, we compressed them, and looked at what happens with the porosity. So a measure for porosity is the volume filling factor. So this is the fraction of the overall volume really filled with material. So we start at about 20% filling factor, and as pressure increases, so as the bodies grow bigger and bigger, or as bigger and bigger bodies are considered, they compactify. And that has influence on the thermal conductivity, on the tensile strength, and many, many physical properties in the inside of those planetesimals. And the result is that at some point, this stress here, this compaction is so high that we are starting to lose the individual pebbles. So a pebble pile where even in the center you can identify the original pebbles can only exist if the diameter of the body is smaller or about 50 kilometers. For all larger bodies, the center is so compacted that they forgot about their pebble origin. So if we want to find out whether this whole model is correct, so whether planetesimals form out of clumps of pebbles, then we should not look at those large bodies, but rather at small bodies. But 50 kilometers is a good size already. Okay, another thing is, so this is the same plot here on the left-hand side as before. Here we also applied compression, but you're seeing this is only a kilopascal, or 2 kilopascals here. So we're considering radii of only a few kilometers, 5-6 kilometers or so in this range. And we measured the tensile strength. So how good is the cohesion among the pebbles? For no stress, 0, the cohesion is on the order of 1 pascal, which is really nothing. That is an important property for comets, as we will see later. But if the bodies are larger, and we're only talking about less than 10 kilometers in size, the pebbles in the center already have a cohesion of 50 pascals or so, and a comet with such a cohesion could not be active. So if we want to understand comets, then we should look at this low compression material, but naturally this is at the outer parts of a planetesimal rather than in the center. So the pressure is at the center. That's not the only thing. The next thing is the planetesimals that have formed in the young protoplanetary disk, so in the first 10 million years, so first few million years. And this is the time where lots of radiogenic short-lived nuclei were there. So aluminum-26 is the one that most people have heard of. So this has a half-life of give or take 1 billion years or so. And and that was inherited by the solar nebula from outside. So if a planetesimal forms early, it inherits a lot of those radiogenic nuclei. If it forms late, it inherits less. And these short-lived nuclei decay, and with a decay, they deposit heat. So they deposit heat into a body that consists, if it's a small body, of pebbles, which themselves consist of very tiny dust particles. So the thermal conductivity within a pebble is low, but the thermal conductivity of the whole pebble pile is even lower. So we have an extremely bad thermal conductivity, and the heat generated in the center is stuck there. And that can lead to the evaporation of ices, to the migration of ices, for larger planetesimals, even to the melting and the differentiation. So we can have, if the planetesimal is small or forms late, so that this process isn't important, we are dealing with an undifferentiated planetesimal. But if the formation is early or the planetesimal is large, then we may deal with a differentiated body. And differentiated not necessarily means an iron core, but it may mean a core that is devoid of volatiles. Okay, again, so this is our view of a planetesimal, so as a pebble pile. And here is our two models for two different radii of the pebble. So this is a millimeter pebble, this is a centimeter pebble. And we have a model of how the heat conductivity goes as a function of temperature for those two pebble piles. And if you're familiar with heat conductivity, typical materials have on the order of unity in watt per Kelvin and meter. So 1 to 10 watt per Kelvin and meter is the normal material. Here we're dealing with less than 10 to minus 3. So really nothing. So much better than air. So air is here. And so then, of course, the radiogenic heat is generated and cannot be transported, so the temperature rises, but that drives as the temperature rises, that drives the radiative heat conductivity up, and this is why the curves go up deeply. This is a temperature to the power of 3 effect. So in the end, at high temperatures, the conductivity is high. And we modeled the temperature evolution, Jürgen Blum modeled it, and he found differentiation, and we modeled it as well in Denver with Uri Malamud from Israel as first author. And here's an example of what happens to a 10-kilometer radius planetesimal as a pebble pile. So with the characteristics of this heat conductivity, after that formed 5 million years, after 4.6 billion years today, so short-lived nuclei, long-lived nuclei, everything taken into account. And here is the fraction of, or the density of water ice. We started homogeneously at 0.1. And in the end, today, such a planetesimal, if it formed 5 million years after CAI, if it was 10 kilometers in size and survived until today, it would have lost half its ice in the bulk of the volume, but the ice has concentrated in a thin shell close to the surface because the surface is cold, the ice cannot escape. And here is the map of formation time and radius. So here is a 20-kilometer radius body. Here's a 1-kilometer radius body formed after 4, 5, 6, 10 million years. And the pie chart tells you how warm they were. And of course, they're much warmer in the center than at the periphery. So those that remained cold under 70 K, of course, are here, small bodies, because then the heat that is generated can escape to the surface and form late, so not much heat generated at all. And those that form early and are large, they are the most affected. So they have reached temperatures above 273 K even. So water can not only evaporate and be transported outward, but it can also melt. And we done a fun study in the lab. So we put pebble piles mixed with ice, put a lid onto it so that we have an equilibrium pressure, like in the inner parts of a planetesimal, and we saw the pebbles even collapse. So something really majestic may happen to a planetesimal, but we haven't thought of that properly yet. I just wanted to tease you here that there might be effects that are worthwhile studying in the future. Okay, so the result of that thermal metamorphism is that it's either unimportant, so our planetesimal after 4.5 billion years is still homogeneous, so it has the same makeup of materials as originally. But large planetesimals and those that were formed early enough to have inherited lots of radiogenic nuclei may be devoid of ice, that is the red color here, in the center, and enhanced in ice in a thin layer close to the surface. And finally, and that happens on the order, because the short-lived nuclei all have lifetimes on the order of a few million years. That happens on a 10 million year time scale. But then there's still 4.59 or so giga years in between this last event and today. And in that time, of course, planetesimals depending on where they are, further in the center, towards the center, or further towards the periphery of the nebula at 50 AU or so, may collide. And those collisions, because the gas is gone, are typically hypervelocity collisions. So we're dealing with hundreds of meters per second or even kilometers per second collision speeds. And that's the least studied. So we have no really good model that is capable of modeling collision of planetesimals that are so fluffy as a pebble pile. So we have filling factors on the order of 20–30%, so 70% or so, or 80% even porosity, and there are no SPH codes available that are trustworthy enough to model that properly. So because we can't do that, or the time isn't ripe yet, we subdivided the collisions into subcatastrophic, the lucky ones that didn't undergo anything really mysterious, the catastrophic ones, which are on the boundary, and those super catastrophic ones that were the unlucky losers here. And just to show you what happens to a pebble pile if it collides with another pebble pile. So again, this is a pebble pile here. 2 centimeters in size altogether, the other one as well. Collision speed 10.7 meters per second in our laboratory proctor in vacuum. So 4.5 grams each. They were pre-compacted at 50 kilopascals, so to mimic a 30-kilometer object. And you see that's completely destroyed at 10 meters per second, which is just nothing. But the pebbles are not heated or so and not melting. They're just dispersed. Okay, so again, we don't know very much. So we subdivided into subcatastrophic. So the pebbles survive. The bulk morphology is preserved. Maybe there's a little bit eroded or so. The ices survive. Into the catastrophic collision regime, the pebbles survive, but the morphology is destroyed. But the ices do survive, and the supercatastrophic remains the same as before. Now we take everything together. So we have the lithostatic compaction for large bodies, or no compaction for smaller bodies. 50, 100 kilometers was the center line. We have the thermal metamorphosis, or no. And we have, of course, the subcatastrophic or supercatastrophic collisions. And if we combine those, we can distinguish between 5 principal types of planetesimals that would be found in today's solar system. Those that are just a little bit eaten up at the surface, but nothing else. These, of course, would be the perfect sources for information about their formation. Then those that are differentiated, those that did some catastrophic collisions. So every single rubble piece here is still the original, but the overall shape is different. Then the combination of the two, and those that we can draw no conclusion about or in terms of their origin. Okay, now this is the introduction. So the formation of planetesimals. There's a variety of possible planetesimals today. Everything is possible, and maybe all the 5 are there at some point. Maybe it's less than 5. The question is, and now comes the second part of my talk: do comets reveal us anything about their formation and evolution and collisions, all that? So I claim here that comets do consist of pebbles. So that would be something that we really learn from comets. If they really consisted of pebbles, we would know that the basic formation scenario, that we first form pebbles, then pebbles cannot grow any further. The streaming instability, gravitational instability kick in, form planetesimals, and somehow the comets are among those 4 here where we can draw still conclusions because they are pebbles and cannot do that. And I think there's 3 lanes of evidence here that pebbles do make up the comets. There's astronomical observations, there's meteor showers, and there's space missions. And I'll run through them one by one. Here's a typical image of the sky in inverted colors, as usual. You're seeing here the comet with its tail. But here along along the sky, you're seeing a black lane, which is called a cometary trail. Cometary trails were only discovered when infrared astronomy kicked in the 1980s. So the IRIS satellite was the first to observe the whole sky in the thermal infrared. And IRIS found streaks, lanes of linear pieces, or of course it's a sphere on the sky or an ellipse or so, streaks with infrared emission. And these were exactly coincidence with the orbits of individual comets. So an individual comet sheds material along its orbit. And it can be estimated that the beta parameter, which is a measure of the size, so beta is the fraction of radiation pressure relative to gravity. So radiation pressure with respect to the solar light in relation to gravity with the sun. So if beta is very small, radiation pressure doesn't play a role. If beta is 1, we are at the regime, it does say it somewhere, well, beta equals 1 is typically a micrometer or so in size. So for the micrometer particles, the radiation pressure and the gravity almost exactly cancel. So they are spread all over the place. They don't follow gravity anymore. For large particles, so beta smaller than 10 to minus 3, they stay where they were formed. There's a little radiation pressure, so that distributes the particles along the orbit, but doesn't bring them away from the orbit. And that the analysis showed that the beta values here are smaller than 10 to minus 3, meaning that they are at least millimeters in size. So that's an indication that comets shed particles of millimeters or larger, which we can identify, of course, with pebbles, the formation pebbles. Okay, meteor showers, the same thing. Now, imagine the Earth crosses on its orbit this path, and that happens with a number of comets, I think on the order of 20 or so, and that leads to those meteor showers that we all have heard of. So an enhanced number of meteors per time interval when the Earth goes through the trajectory of a cometary orbit. And these meteor showers can be analyzed, and relatively recent work by Peter Jenniskens in California shows the meteoroid diameter here in centimeters. So here's 1 centimeter as a function of the interference speed. Doesn't matter very much, but the order of magnitude again is centimeters. So the typical meteor shower meteors that we're seeing when the Earth crosses a trail is on the order of a centimeter. Again, the petal sizes. They could also show, and it could also measure the densities. That's remarkable that you can, by analyzing the meteors in showers, you can find out the density. Here's the density of the meteors. So it's 10 grams per cubic centimeters of metal or so. Here is 0.1, which is a very fluffy particle. And as a function of semi-major axis. So basically on the left-hand side is the Jupiter family comets, or amongst them are the Jupiter family comets. And the long period comets are here on the right-hand side. We're seeing here a large number of solid materials and some pebbles that have densities of smaller than the material density, so fluffy material. But the fluffier material, certainly with densities of roughly 0.5 grams per cc, come from the long period comets that are from the reservoir of the contemporary Kuiper belt. So the Kuiper belt would probably be the source to look for authentic planetesimals today. So this is an indication that we have the right size and the right porosity in comets, not necessarily the Jupiter family comets alone, but in comets in general. And the final piece of evidence that I would like to present you is the missions. So we have evidence for pebbles in missions from basically all the space missions that went to the comet. Giotto, Stardust, Epoxy, Rosetta, you name them, all have found that the size distribution that their individual dust detectors measured is top-heavy. So, for instance, Stardust collected dust in aerogel at its flyby of about 6 kilometers per second, and the single biggest particle has half the mass of all the particles collected together. So it's top heavy. Some years ago, we analyzed Rosetta data, and the typical size we found is this hatched region here is a radius of roughly 0.5 millimeter or 1 centimeter diameter. And that explains all the individual observations by different instruments, all the red bars here. It measures the streaming instability theory and also the observations of probabilities at the time. So there is lots of evidence that comets, when they come close to the sun and become dust active, that most of the mass they're ejecting is ejected in pieces of dust that have the size of a pebble and also the porosity of a pebble. So they might be pebbles, of course, that's not a proof. The composition is difficult. So Bardin et al. Had analyzed measurements from also from Rosetta. So they find roughly 50-50 between minerals and organics. So and that's still an unsolved mystery. Why is so much organics there? And what is the average density of the organics in order to interpret the fluffiness of Comet 67P, whose density is roughly 0.5 grams per cc? How can we reconcile this with all these measurements? So there's many open questions still. The case is as the 3 components of the composition. Marco Fuller has developed a model that there is even internal structure in the petals, because only in that way, so internal structure, meaning we coagulate the grains into fractal agglomerates. The fractal agglomerates are compacted into something smaller than 1 millimeter, and those come together and form the pebbles that are then on the order of centimeter. So we have a 2-step hierarchy inside the pebbles. In that model, they could explain the observed activity in dust and gas also, and only in that, and this is the model here, and only with such a structure. So this is an open question whether this model is correct or not, but there's people working on the internal structure of pebbles even. Okay. I just said that there's evidence that when comets come close to the sun, they shed most of their mass in dust in forms of pebbles, so large particles, top-heavy size distribution, mass distribution. The question is, why do comets then have dust tails at all? And if you have never asked that question, I'll let you know why I doubt this. Comets should not have tails. The reasoning is very simple. In the tails, the dust size can be measured. This is a mass spectrometer, if you like, because of the radiation pressure, the beta value I indicated earlier. We see it's a nice graph of the beta value. So beta is 1 here, and 1 here is 0.6 microns in radius, so a micrometer particle. Radiation pressure blows it exactly away from more or less from the sun. As beta increases and decreases, so the dust growth is bigger and bigger, they follow just the trajectory. Here's the trail, here's the tail. So the tail has micrometer sizes as the canonical size. So micrometer size has tensile strengths. If you imagine a clump or a pebble, the internal structure of a pebble of micrometer particles has an internal tensile strength on the order of a kilopascal. So we've measured lots of these samples in the lab. So as a function of particle radius, here's a micrometer, here's a tenth of a micron, here's 10 microns. We measured the internal tensile strength at a porosity of 50%. And you're seeing we're in the range of 1 kilopascal, 10 kilopascals or so. So on the order of a kilopascal or more, as a function, this is a strong function of volume filling factor, so 1 minus porosity. So here is the 1 to 10 kilopascal range. If the porosity increases, so filling factor decreases, we're going down, but the smallest we could measure is 100 pascal. So this is the range of cohesions. However, if you do models of what the gas pressure is, and the gas pressure is the only source that we know of at the moment to drive out the dust, to form the dust. And the gas pressure has to work against the cohesion, so the gas pressure has to exceed at least 100 pascals. And all the models we have ever done, and most everybody has done, estimate the pressure on the order of 1 Pascal. Here, on the order of 1 Pascal. So hardly anybody, except for very, very specific internal structures of pebbles, can ever reach anything in the order of 10 Pascals, not spoken of 100 or 1,000 Pascals. So why do comets then have tails? And now, of course, I'm a laboratory person, so we're coming back to the laboratory. So we built up many, many years ago with the help of Günther here and people from Bern as well. We built up the COFI lab, the Comet Physics lab. And so we wanted to study the mechanism behind the ejection of dust, because the conundrum, the question, why do comets have tails, was known to us then already. So what we started with is pure ice. So we made a comet, artificial comet in the lab, that consisted of micrometer-sized ice grains. We can produce them in large quantities. So here's the scale. This is 20 microns. So the average diameter of an ice grain is 5 microns. It's fluffy, very fluffy, and shiny white. So we brought them into vacuum and shone some artificial light onto it. And to our surprise, we just wanted to take that as a calibration measurement. To our surprise, I hope you can see it. It becomes dust active. There's no dust inside, it's just ice. So we shine light on it. It throws out, it evaporates, of course, because it absorbs in the infrared some of the energy, but it throws out particles as well. And the fraction of particles thrown out are the dots here, is on the order of 20 to 40%. So 20 to 40% of the mass that we're losing here goes out into solid particles, and the rest, 60 to 80%, go out as evaporation, as we had anticipated. And that was, we had to understand that. Where does that come from? The idea is the following. So here is our artificial comet, just consisting of ice. So the blue color doesn't mean nothing at the moment, so it's just ice. So we shine light onto it, and that light penetrates very deeply. So we've calculated about 100 to 1,000 of these layers deep. We are basically at the same temperature. So all is at the same temperature. So all the particles evaporate slowly into vacuum. The environment is vacuum and it's cooled. So all the particles shrink. And of course, the smallest ones shrink faster because they have larger surface to volume ratio. So at some point they are gone. So you're seeing that particle is no longer here. All the small particles are gone. So if we just in this plot just have 3 sizes, the smallest are gone first. Then come the next and the next, and so on. And this cluster here, and this is why it's marked blue, this cluster has no contact anymore. So we ran a simulation in 3D, of course, with a steady size distribution, not discrete, like here. And we found that as a function of filling factor, as a function of the packing here, what the fraction of emission in particles relative to the emission in gas would be. And you're seeing it follows a very steep curve. The fraction here between 20 and 40% is what we measured, and this volume filling factor roughly matches what the volume filling factor of our sample. So we have a new mechanism of how a comet can emit particles. Of course, this is ice particles, but the comet, we know, emits not ice particles, at least not a lot, but dust particles. So we had to take that model and convert it into a dust emission model. And now we're coming back to the question of how are these dust particles look like in the solar nebula. And there's 2 ideas. So we have dust particles, that are the red ones here, and we have ice particles. They are mixed intimately. So that we have dust particles and we have individual ice particles packed together. Or The other idea is the dust particles form first by condensation, and then the nebula cools down, and then the ice condenses, and of course it condenses on the surfaces available. So the ice condenses on the surface. So we programmed these two models. We ran these simulations. I show you examples. I start at the right end, so the ornamental particles. The color is just a measure for the size, so it's a size distribution. And it says periodic boundary conditions, so it's just the surface layer, and you're seeing it all goes away. And for this model of core particles is completely independent of the dust to ice ratio. So as long as on every dust particle there is a thin ice layer, it doesn't matter how thin, as long as there is an ice layer on each dust particle, this process works. If the comet would consist of core ice particles entirely, all the mass the comet sheds would be in small dust particles. That's not what we're seeing. But most of the dust emission goes into pebbles. This process doesn't produce pebbles. Even if you make pebbles, it doesn't produce them. So we can rule that out. So I'm pretty sure the dust particles in a comet are not core particles. Okay, let's come to the next model. So the intimate mixture. I'll show you a movie. Now the one color is the dust, the other color is the ice. I forgot which one is which, but it doesn't matter. All the ice evaporates and the dust is released. That works. But it doesn't work for every dust to ice ratio. So here is the blue was the dust, the yellow is the ice again. But now I show you a dust to ice ratio that doesn't work. So again, the blue is the dust, the yellow is the ice. And first a few dust particles are emitted, but then the ice retracts faster than the emission, and the whole thing dies out in terms of dust emission. So only gas, no dust. This is what the comet does. It emits some dust, but not a lot. Okay. So the question now is, why do comets have so very little ejection in dust? So most of the mass goes into pebbles and little in dust. Unfortunately, we don't know quantitatively what that means. Nobody has ever tried to measure or derive the fraction of dust and pebbles. This is really an open question. It's only known it's little dust, or whatever that means. So whether it's 10% or 1% or per million, I have no idea. We tried some years ago to analyze Rosetta data and came up with size distributions of the dust. They all top heavy, but also quantitatively, it's really hard to tell. So if you believe our new model, and that paper is just submitted, not even reviewed yet, so there's still concern about that, but if you believe there's some truth in it, it means that the cometary grains cannot consist of core particles because it would only emit dust and no pebbles. For intimate mixtures, the dust to ice volume ratio must exceed a value of 3:2, or a dust to ice mass ratio on the order of 3, which is what most people predict for Comet 67P, at least, a dust to ice mass ratio on the order of more than 3. Recently, on 67P, the so-called WABs were discovered. WABs stands for water-enriched blocks, which you can see even by naked eye on the Rosetta Osiris images, because they are shiny white. The rest of the comet is pitch black, and that is shiny white here. And these WABs are on the order of a few meters in size. They are long-lived, so they can live for many, many days or even weeks. And people are trying to estimate the dust to ice mass ratio, and it is on the order of 2, which is below the critical number of 3. So the WABs could be the source of the dust in the tail of a comet. I don't claim that this is the case, but here is a candidate at least. So most of, following that China Yellow paper, 2022, most of the mass of a cometary body does have a dust to ice ratio that is large. I doubt that the 50, but larger than 3. And only a few percent have this small value. And that would explain qualitatively why there is more mass in the pebbles, in the trail of a comet, and less mass in the tail of a comet. Okay, here's a picture of the web from the original. Okay, I don't know, this has proceeded a lot, so I skip that point. I come to my conclusions. So this is a nice movie on Comet 67P, how we could reconcile it. And this is a Chiba image of close by image of the surface of Comet 67P taken by the Philae lander. And the typical things you are seeing here are 1 centimeter in size. Those could be the pebbles. So this is your only chance to see them ever, at least in my lifetime. I doubt that we will have a cometary landing or a sample return mission ever again in the next decades or so. So I conclude that comets seem to be consisting of pebbles. Here is kind of the evidence, if you like. But there's more evidence from the cometary trails, from the meteor showers, from Rosetta observations, all indicates that the most of the dust mass that goes out of a comet when it's active goes out in pebbles, and that confirms the pebble pile collapse law. Comets are inhomogeneous, despite their radius measurements that tell us on the order of 10 meters or larger they're homogeneous, but they might be on the order of meters inhomogeneous with the webs, water-enriched blocks, wherever they come from. I have no idea. So they might have, with a volume abundance of a few percent, these water-enriched blocks, which are the sources for the cometary dust tail particles. The particles cannot be of core metal type, so that restricts the formation of the ice particles to a region where they have not found too much surfaces that of large particles, at least they could coat. And that there is some mixing of dust and ice afterwards before the planetesimal formed. I think I said that. I said that too, and I didn't mention that. So the take-home message is a comet nucleus is like a sand pile. It has a very low packing density, or a low packing density, lower than a sand pile, because the sand grains in a comet are the pebbles that are porous themselves. It is relatively homogeneous, with the exception of the webs, for instance. It does have large pore space. The gas comes out rapidly. It has low strengths on the order of pascals, otherwise the pebbles could not be ripped off. And it has a very low heat conductivity, which resembles the surface temperature. The point is, a sand pile is at the end of what we can explain with physics. So here is the complexity in physics, or difficulty in physics. So Newton's laws for most of us is still comprehensible. Special relativity, yeah, maybe. Here is, of course, who understands quantum mechanics. I think Nature yesterday or today says, or last week, I think, says nobody understands quantum mechanics. Even today, general relativity is the same level. However, this is not the end. A sand pile is where we are if we want to study comets. So granular matter is a really complex material, particularly if there's water ice involved, because water ice is one of the most complex materials per se. And with that, here's my conclusion again as a picture I've shown you at the beginning, and here's my acknowledgements. I would like to thank you for your attendance and your attention, and I'm ready for questions. Thanks.
Yeah, well, thank you. I really enjoyed it. Are there questions? Let's see. Raise hands.
I didn't quite understand why these particles seem to be quite accelerated in these experiments, in the initial ones where you illuminated this kind of rubber pile, and somehow they got out very quickly. So what actually does the So I can only imagine it's a kind of heat, so there's no directional thing, let's say. So what does the acceleration?
Okay, I certainly didn't properly explain it. So we have this micrometer ice particles, and which we illuminate, and by the absorption of the infrared bands of the ice, it becomes a little bit warmer in a vacuum environment. And with getting warmer, it starts to evaporate. So there's a gas flow. This is the 70% of emitted of lost mass is in gas. There's a steady gas flow that goes vertically up, and that basically does the acceleration you were seeing in the movie.
Right. So the key is that these pebbles kind of you first destroy the bonds between the pebbles rather than the pebbles themselves, right? So once they are kind of getting free of the environment, they stay as a pebble and are accelerated.
I was talking about dust grains, but the same is true for pebbles. So, but the pebbles have not kilopascal cohesion. Pebbles have 1 Pascal cohesion. That pressure can be reached. So you can overcome. You don't need to have that evaporation of the ice between the pebbles. Not necessarily. Doesn't mean that it doesn't exist. But the pebbles you can rip off with a gas pressure. The dust you can never rip off, but you can only accelerate once it's liberated by the evaporation of the surrounding particles. That's my idea about it.
Do we still have time?
I have time.
Okay. So yeah, thanks for a really nice talk. You give a really nice summary. Unfortunately, I'm more interested in growth of planetesimals to planets, something like that. So what's your opinion on like the current theories like pebble accretion or planetesimal accretion? What do you think?
Yeah, so I was very happy when I first heard about pebble accretion, though, because all our efforts over decades ended in forming pebbles. So when Anders Johansson or Newton and Goodman first invented the streaming instability, and Anders Johansson and colleagues showed that it can lead to 100-kilometer planetesimals, I was very happy because, first of all, once you started with a classical theory, 1-kilometer sized planetesimals took ages to form anything. So that was the first step, was the strongest step was already done. But then still, the formation of giant planets still took very long, like millions of years, where we all know that the giant planet needs the nebular gas to be around, and the typical lifetime is on a few million years, maybe up to 10, but on the average, maybe 3. So you better form that early. And then pebble accretion came as, of course, a natural product. So only canonically half of the pebbles are converted into planetesimals. The other half is still around. And of course, because of the gas friction, they're drifting inwards. And once they encounter a body that has formed already with an extended atmosphere dragged along, then they are very efficiently accreted, and that solved the timescale problem, at least. So I was very happy to hear that. And to me, it's more efficient than planetesimal accretion. But yeah.
Okay, thanks. So, Gabriel first.
So if the Rosetta comet was so loosely bound, why is that the philae bounced off and not sinked in?
An extremely good question. Let me come back to the sand pile. Sand has exactly 0 tensile strength. Have you ever stood on a beach? Never. So compressive strength has nothing to do with tensile strength. That distinguishes granular matter, like sand, that shows that we're here, not there. That distinguishes granular matter from normal matter. Normal matter, there is a relation between tensile strength and compressive strength. Sand is the extreme opposite. It has as much compressive strength as you like. You can send everything on a sand, but you need no force to rip it apart.
What would be the effect of laminar or turbulent flows on the structure formation?
In the phase where the planetesimals form, yeah. I can only rely on theoretical work here. Laminar flow means that the collision speeds are dominated by the drift. So a large pebble drifts faster inward, sediments faster, and has a different azimuthal velocity than a small pebble. If there is turbulence in the gas, there comes on top another collision source. And typically, if the turbulence strength is high, so an alpha number 10⁻² or so, then the collision speeds are so high that the maximum pebble size is smaller than without turbulence. So as turbulence increases, typically the pebbles become smaller.
And what about viscosity?
Viscosity, but viscosity only were in the Knudsen regime of the pebbles. So viscosity is not an issue here.
Not an issue.
Yeah.
It's a question to which extent hydrodynamics is applicable in these large-scale conditions.
Okay. Yeah. I'm not the expert on the principles of hydrodynamics here.
It's an issue of the typical scale.
Yeah.
One more question on the compression and tension. You in your experiment, you throw two aggregate of pebbles and they splash into pieces, right? But this is when compression, the same as philae landing on the comet.
Oh yeah, but this is unconfined. So these were finite pebbles. Philae landed on an infinitely large.
The ratio of size is to.
Yeah. This makes the difference. So that's true. If your beach would be a height of sand, a very tiny one, and you step on the tip, then it spreads. So this is a geometrical point.
You said you expect for the refractory material, you expect tensile strength of 1 Pascal, approximately.
On the pebbles.
On the pebbles, yeah, for the agglomerates. So if you now add water ice, and the water ice can also be deposited in the pores of the agglomerates, then the tensile strength can be much higher, isn't it?
The internal tensile strength, yes, if you post-deposit water vapor into the pebbles, then yes, then it can go to megapascals or so. If you just take ice particles and dust particles, their surface energies are not worlds apart.
We have sublimation and deposition again. So a good contact between ice particles and agglomerates of the refractory can be ensured, and then tensile strengths can be much higher.
That is true.
If tensile strengths are much higher, then enclosed caves can build where, due to sublimation, the pressure can reach much higher values. But then you can burst out much greater pebbles.
I made the same argument
as well. So this opens the possibility of emitting a lot of different ranges of particles, particle sizes, which are actually measured.
Yeah, that is true. I had the same argument. I've never seen any thorough calculation of that, a modeling. So nobody has convinced me that this hand-waving argument, which I did myself, really works. And it's complicated. So it's something for the future. The next proposal we're writing is maybe about that.
So I think for one short question, Daniel.
All right, okay. Thanks. Thanks for the very interesting talk. One question, if you go to the next slide. So does this scenario of forming the pebbles to this planetesimal also hold for asteroids?
Oh yeah, it does. Sorry, I was concentrating on the comets. This form, and typically asteroids are, the planetesimals are larger than 100, or give or take 100 kilometers, or maybe up to 1,000. Then they are, first the pebbles are destroyed by lithostatic stress. And then, and many works have done this in the past already, in the past decades. These short-lived nuclei then lead not to the differentiation of ice against non-icy material, but of course to a real differentiation in the original meaning of the word, so that we have differentiated planetesimals of a few hundred kilometers or so. That certainly works also for the non-icy or less icy material in the asteroid belt. But then this part in the asteroid belt is always here. Because the collision speeds on average are 3 to 5 kilometers per second, there's absolutely no chance for any ice or any fluffy material and ice and lots of ice to survive here. Whereas in the Kuiper belt, we're more here. And this is why we have no comets from the asteroid belt, or no planetesimals left. So even the largest Ceres or so is a planetesimal, but Ceres is a planetesimal even worse than that because it was even more. Yeah, thanks for the questions.
Yeah, thank you very much for your nice talk. Also for the and you will be around here some